Okay, aloha student, welcome back to Math 100. We are in the last section of this chapter, probability. Okay, so this section is going to be hard, but bear with me. Hopefully, we can get more familiar after the examples. Okay, so last time, 13.3, we went over conditional probability very briefly. Okay, so this new notation that's P parenthesis with E and then vertical bar F, that is read as the probability of E given F. So given F means that F already happened, so 100% you know F is already happened. And so what does that mean? Means that it multiply our new sample space. Okay, so to a new sample space if we have a dependent event. Okay, so what does that mean? We'll have more example, okay, later. Okay, dependent event. Dependent event means one event affect the sample space of the other event, right? So that's dependent event. If it doesn't affect the sample space, the whole, you remember what sample space is, the whole possible outcomes. If it doesn't affect the whole possible outcomes, then it is an independent event. So given or not, then it doesn't matter, right? So in pictures, we always like to compare to pictures. So if we have a probability of the event, how is that different from probability of the event given F? Okay, so they are actually equal if it's independent event because its probability of E is not affected by F. So in picture, if we have a sample space, right? So probability of the event is always the probability of that event E. E is a subset of this whole sample space S, right? So probability of event E is the cardinal number of the event E over the cardinal number of the sample space. And if it's an independent event, if F happen or not does not affect the sample space, then it's equal. But sometimes it's affecting it, right? So if it does affect it, then our F, happen or not, affects E, and this means our new sample space will be restricted to the F. Okay, so given F already happened, so F will be our new restricted, I would say new restricted sample space. Okay, new restricted sample space. And so that will be in our new denominator, right? Because no longer are we looking at the whole sample space. If it's dependent, then our sample space got restricted to only looking at the F. And so the probability of the E is only considered a part of the E that is in F, right? The part of E that's in F, remember the event had to be in the sample space, had to be a subset of the sample space. So if our subset E is only, it's only the part that is containing our new sample space is this little part here. And in chapter 2, we say that this little part here is E intercept F, right? So our cardinal number of E intercept F will be our numerator, right? Because again, we are not going to consider the whole E because our new sample space is only this F here. So our E cannot be outside of our new sample space. So only consider the E that is within that new sample space F. Okay, so sound like I'm speaking a foreign language. Okay, so let's look at this example here, so hopefully it makes a little bit more sense. Okay, so if we have this event E, that when we are rolling a die, remember when we roll a die, our sample space is equal to 1, 2, 3, 4, 5, 6, right? So you have 6 elements in the sample space when we roll the die. And so this event is a subset of the sample space that's fitting the description of even numbers. So that's going to be 2, 4, and 6 only, right? and this F is another event, right? And so the F is row a number that's less than 4, and in the sample space of 1, 2, 3, 4, 5, 6, we have 3 numbers that's less than 4, which is 1, 2, and 3, right? 1, 2, and 3, right? So if we are only rolling a die, not 2 different dice, so then this is, have 2 characteristic is saying, what this is saying is, what is the probability, okay, probability of rolling a, E is an even number, right? An even number if, given is the if, we know already for a fact it is a number less than 4. Okay, so that same die, if we already know it is a number less than 4, so we are restricting it to the the subset of the whole sample space of 1, 2, 3, 4, 5, 6. We are restricting it to only the number that's less than 4. So our denominator is going to be just the F, right? Because we already know that number is less than 4. So that's only 1, 2, 3. So out of the 3, right? Out of the 3, because we are not looking at the whole sample space anymore. It's restricted to that given, the givens if we already know, right? That's the given. And so the numerator is supposed to be E, but the E had to be the part of E that is in the new sample space, right? This is the new sample space, if it's a given, right? So new sample space. And so not all of E, not all 1, 2, 3, 2, 4, 6 is in 1, 2, 3, right? Not all of E is in the F, right? So only this number 2 here of E is contained in our new sample space. And so that's what we call the E intercept F, right? So the part of E that is in F is only the intersection, and so that is the 2, and cardinal number of that is 1, and so that's why probability of E given F is 1/3 in this case, right? So again, this given is our new restricted sample space, okay, new restricted sample space. So if the sample space doesn't change, then it's an independent event. If the sample space change with the given, then it's a dependent event. Okay, so that's the bulk of the idea here. And so that's summarizing these 2 major concepts in this section. One is called the multiplication property, and one is called the addition property. Okay, so the multiplication property is when we have the and. Okay, so it's almost like the chapter 12 when we are doing the fundamental counting principle. We say if we have compound event E and event F, when we are counting, at that time we don't have a denominator, we will say if we have M choice for event E and N choice for event F, we will multiply it together, right? We will multiply it together. That was fundamental counting principle. And so our total possible outcome will be M times N, whatever that number multiplied to be. So this multiplication property for probability is almost what I call the fundamental counting principle for probability. You still multiply them together whenever you have N, okay? So the different cases, what we multiply will be different. So in this case, this means our denominator got changed, the second event denominator changed, and so this is the dependent event. The second event got changed. The sample space got changed by the first event, so that's a dependent event. Okay, so this is the formula for the dependent event, and this is the formula for independent event. Okay, and even with the T, can spell sometimes. I need help with English. Okay, so depending on whether it's dependent or independent, okay, this part here, that is very similar to the fundamental counting principle, but except is what? For probability, right? So the only part that is kind of hard to understand is the dependent one. Okay, the dependent one is when your sample space or your denominator got changed. So your denominator is no longer the same number. Okay, so that one we need to take some practice and hopefully we'll get better at it. Okay, so the next one is the or, right? So the or in mathematical notation of the symbol is the union, right? So this is something we know from chapter 2. Okay, so the union is the or, and or means you have two cases, E and F, right? So if you were to union them, then that's this whole two circle, right? But remember, we don't count it twice if it's the same element, right? We in chapter 2, if it's the same element, we don't count twice. So the probability of the event, if we count it, that means we are finding the probability of this out of the whole sample space, E, right? Out of the whole sample space S, right? And then if we count the F, again, the probability of the F, and if we count them separately, what happened is we count this over that part, we count it 2 times because we count it separately. When we add them separately, we count this middle part here 2 times. And what do we call this middle part here? Is the E intersect F, right? So when we do the union, we only count each element or each probability once, right? So if we had count something 2 times, we need to use subtraction here because the opposite of addition is subtraction. We need to use subtraction to take away our overcount, right? So that's why we have to subtract this. This is what we call the overcount. The part that it was counted twice because we counted circle, separately. We're supposed to only count it once, but we counted it 2 times, so we take away 1 copy. Okay, so again, when we have n, we use multiplication, and again, sometimes the denominator do change in the dependent event. In the independent event, the denominator or the sample space doesn't change, but it's multiplication either way when we see n. But when we see or, then we will do the adding, but make sure that you don't count anything twice by looking at, is there anything that I count twice? Usually is the overlap part, right? The overlap part. And so that's the n. And so we'll come back to this formula back and forth, okay? And make sure you know when to use which one. Is it the n or is it the or? Okay, is it the n or is it the or? Okay, so let's get to the practice question here. Okay, so when you roll a die 2 times, right, or roll 2 die, so this is die 1 is an event, and then die 2 is another event, so you roll the die 2 times as a compound event, right? So you want to know the first die being a 1 is this, right? And its second die being a 1 is again like this, right? And you have, so this is in terms of the mathematical notation, that's what they are asking. First one being a 1 and the second die being a 1, right? And so then it's probability of the first die being a 1 times the probability of the die being a 2 because it's an n, and also because it's a independent event if you are rolling a die or 2 die, a die twice or 2 die. Why is it an independent event? Because your sample space still have 6, right? You still have 6 to choose from. Every time you roll the die, you don't lose a choice. You still have 6 possible outcomes, and so that's independent event. So we can just use an n. So we will just use 1/6 times 1/6, and that will be 1 out of 36. Okay, this is just by formula. Okay, so how does that look in terms of visual, right? How does that look in terms of visual? So we can look at this die. If we are rolling the die 2 times, if we are rolling a die 2 times, right? And so what happened here, the red one is the first die. I purposely make it vertical, right? So the red one is the first die, and the white one is the second die, right? So you're rolling 2 die. And as you can see, these are all the combination. This first one here, first choice, is this one is what, first one being 6, second one being 1, and this one first one being 5, second one being 1. So if you count all of them up, what happened is what? There is 36 of them, 36 combination, 1, 2, 3, 4, 5, 6, right? You have 6 each row and you have 6 columns, so altogether you have 36 choices, right? So which one is the first die being a 1 and second die being a 1 again, right? So it's this one is what we want, right? So this is the one that fits the description, first one being a 1 and second one being a 1. So 1 out of 36 choices in our sample space that is fitting the description that we want. Okay, does that make sense? So sometimes if you have hard time following the formula, sometimes maybe to draw it out, have some visual representation, or look up in the internet how does rolling 2 die look like, right? So you can kind of, oh, okay, that's how it look like. So only this one here work, right? So 1 out of 36, that's why we have the answer that way. Okay, and hopefully that makes sense. Okay, how do I get out of here? Okay, I'm going to minimize this and come back to the, exit drawing. Okay, this number 2, okay, so that's why the answer for number 1 is 1 out of 36, because we have 36 choice in rolling 2 dice, and then only one fits one, first die being 1 and second one being a 1 again. Okay, so second problem is a single card is drawn from a deck. Okay, so if you want, you can pull out the deck of cards, right? And you wanted what's the probability of it being a heart and a ace, right? So we have, this is a simple event, right? So this is going to be 52 cards, right? Simple event, 52 cards, right? So we can count the 52 cards if you can pull out the cards from the internet. But let me do the formula first, because this is a OR, right? So OR, then we're going to do the union, and OR is addition property. So we're going to use H for heart and ace for A for the ace, right? So H union A is what we want, and the formula, the second formula in the addition says probability of H plus counted separately probability of A, and then subtract the one that is what, counted twice, which is the heart and the ace, right? So we have 13 cards out of the 52. That's hard. And ace, we have what, 4 out of 52, right? So is there any card that we counted twice? We counted as a heart and as an ace 2 times, that we're supposed to only count once, right? So ace of heart is the one that we counted as a heart and also as an ace. So that's one card that we counted 2 times that we need to subtract, right? So that is what, 13 plus 4 is already same denominator. 13 plus 4 is 17, and then subtract 1. That is 16 out of 52. And we can certainly simplify that. How does that simplify? I think is you divide by 4. Is that divide by 4 top and bottom, right? So we get 4 out of 13. If you don't know how to do that, you can ask decimals to help us, right? So make sure we box the answer. And also, if you can get some visual effect on the cards, that will help, okay? That will help. So this is what I have in the search on the internet. We have which one is the heart, right? So we counted the 13 hearts here, right? If you count this, all these are hearts. And which one is ace, right? So this is 13 hearts I can draw here, right? So that's the 13 hearts here, right? 1, 2, 3, 4, 5, 6, 13. And also we counted the 4 aces here, right? So did we overlap? Did we overlap or count it twice? That's ugly, right? So this is four aces here that I counted. So which one is the overlap right here, right? So this is the overlap, right? So make sure that you subtract this ace of heart that was counted twice. So this is the 4 here, and that's the 13 here. But this one here was counted twice. That's why we needed to subtract it. That's why we needed to subtract that one. Okay, so those of you who need to look at it, don't be afraid to look up in the internet and look at how does a deck of cards look like and what are we talking about here, the ace, what does the ace look like. Okay, so look it up, spend some time, look it up. This next exam is take home, so you have all the time to look it up. So make sure you understand it instead of trying to just follow the formula. Okay, and I hope that helps. And we hope to just get back to the next problem. Oops, how do I get out of here? Exit drawing. Okay. I don't want to save. Oops, what did I do? I think I just exit out of our okay, made a boo-boo there, start over again. Okay, so what question were we on? We were on, okay, start over again. We were on this, yeah, number 3. Was it number 3? No, it was number 2, the hot end, right? So I have to rewrite it again. This is probability of heart or ace, right? So it's probability of heart, right? Remember? And we have 13 out of 52, and then probability of the ace, and then you make sure you take away that overcount, right? And how come we cannot do the multiplication like the first one, right? For the n, how come we cannot do the multiplication for the n? Because when we are choosing one single card, they are not independent. Two characteristic, they are not independent. That's why we have to look at the card, right? So that's the 4 out of 52, and we have to look at the card. We couldn't. This is not equal to probability of the heart times the probability of the ace, like number 1. It's because what? This is not independent, right? This is only for independent only. So in our case, this is not independent if you are doing just one card, right? One single card. This is 2 separate die in the first problem that you wanted. The first die being a 1 and the second die being a 1 is 2 die, so that was independent, remember? So we could kind of multiply them together. So I made a boo-boo, but then we can revisit that, right? 16 times 16 was 1 out of 36. It's because it was independent, right? So make sure you know the difference between the 2, right? Independent, not independent. Sometimes you have to go and do it logically, think about what does that mean? What does the overlap mean? Sometimes you can just change the denominator, but here you have to use logic to think about it, right? So make sure you don't just automatically assume the n. You can use multiplication only if they are independent, only if they are independent. Okay, so number three. Okay, so again, we are choosing, we are rolling only one single die, right? Not 2 separate die. So if it's not 2 separate die, it's not 2 independent event. So this is one that is dependent. Okay, so let's see if event E is out of the sample space of 1, 2, 3, 4, 5, 6 for rolling a die, right? And E is a number out of that 6 number, which is 1, 3, and 5, right? And then you have this E. E is a number that, out of that possible sample space, out comes the one less than 5 is 1, 2, 3, and 4. Okay, so looking at part A and part B, are they asking the same question? Okay, are they asking the same question? So this is the different given, right? This is given F for part A, and so your multiply sample space is the F, and this is given E, right? So it's given is different, so your multiply new restricted sample space in this part A is F, right? And in this part B is E, your restricted new sample space is different because the given is different. So this two is going to be different fraction, right? So this is the part of E that's in F, right? So the part of E that's in F is also called the E intercept F, and the part of F that's in E, that's the F intercept E, but they should be the same, right? They should be the same. E intercept F is the same as F intercept E, but given is different. Given change the multiply restricted sample space, so denominator is different, right? So for this part A here, our F is what? Our F is cardinal number of 4, and our E, the cardinal number is 3, right? So this 2 is still two different denominator. But the element of E that's in F for part A is 1 and 3, right? 1 and 3. So two element that is in E that is part of F is 2. And so part of the element that's F that's also in E is also 2. So the numerator is the same, but the denominator change because of the given, right? Of the given. Given is the one that is restricting the new sample space. So what is part A and part B saying is the order matters. So E given F and F given E is two different things. You cannot mix it up, right? E given F, probability of E given F and F given E is different. Okay, so the answer for the first one is half, and the second one is just 3/2. Okay, so make sure you understand the given restrict the sample space, and so if it's different given, it will be different denominator. Okay, so for number 3, part C and part D, the probability of E and F, the probability of E and F is the E and F, the cardinal number of E and F, and because there's no given, there's no restricted sample space, so it's still the same old sample space of 6 numbers, right? 6 numbers in the row of die, and this E and F is, again, we counted that was the the 1 and 3 was both in E and F, right? So then that is reduced to 1/3, right? And so same thing here is saying that you can switch order if it's an N, if it's not a given. If it's not a given, you don't restrict the sample space doesn't change, so still the same sample space. So F in the front or E in the front, it does not matter. For the intersection, it does not matter, but for the given, which one is in the front matters. And so again, this is what C and D is trying to tell us. E and F and E is the same, but E given F and F given E is different. Okay, so that's what these 4 questions trying to tell us. Hopefully that makes sense. Okay, so number 4, again, if you are rolling one die is with 2 characteristics, that's dependent event, but when you're rolling 2 die, the two dice are separate, so this is independent event, and independent event help us because we can use fundamental counting principle on probability if it's independent. Okay, we can count them separately and just multiply them together. Okay, so this one is asking you for probability of A and B, right? So multiplication applies when it's an and, right? Multiplication applies. If it's independent, it's easier, right? So it's just probability of A times probability of B. Then we can use fundamental counting principle on probability, right? So the first one, you have what? How many out of the 6 choices for the die is a 3? You only have 1, right? So you only have 1, that's 3. But the event B, the second toss that is less than 5, it's going to be what? 1, 2, 3, and 4, right? So that's 4. So this is going to be 1 out of 6. Right? And then the other one is going to be 4 out of 6. And so top times the top, bottom times the bottom for multiplication in fractions. So 1 times 4 is 4, and 6 times 6 is 36. And so 4 out of 36 can be simplified to be 1/9. Okay, 1/9. And so 1/9 is the answer for number 4, and we can use fundamental counting principle on probability for independent event. Otherwise, dependent event, we have to kind of, it's a little bit more complicated. So have to think differently. Okay? All right. So number 5. Okay, so we are choosing 2 hearts in a row, right? So the first one, I'm going to choose a card and then replace it. Replace it means I put it back, right? So there's 52 cards in a deck of cards, right? Remember we showed you the deck of cards? So 52 cards, right? Diamonds and hearts and then clubs and spade, they all have 13 each, right? So if you put it back, that's what replacement means. Your second card still have 52 to choose from. You still have 52 to choose from. So that means what? My denominator didn't change. My sample space is the same, so that's independent, right? Independent. So my probability of first one being a heart and second one being a heart, again, if it's independent, I can use the fundamental counting principle for probability, right? So that would be this, right? And so that is, again, how many hearts? 13 out of 52. And then because you put it back, you still have 52 cards, right? So still 13 cards because you put it back, and so that's 52. And each one, 13 out of 52, simplify to be 1/4. I can simplify first and then multiply, or multiply and simplify, doesn't matter. So that will be 1/16. 1 times 1 is 1, 4 times 4 is 16. And you can use the decimals to do the simplifying if you were to multiply first. Okay, does that make sense? And so independent, identify its independent is very important so that we know which method to use. Okay. Okay, so number 6, we are choosing between the multiplication and the adding, right? So here, this is OR, union is OR, and if it's OR, we are going to use the addition property, right? We're going to use the addition property, and that's like probability of A, counting the probability of A, and then counting the probability of B. And if you are counting the probability of the two A and B separately, there is a danger of counting this part here and counting that part here, the overlap 2 times, right? 2 times. And so you want to make sure that you subtract the intersection, which is the N, right? The N, right? The N. And sometimes we need to take a picture of the, whatever that's happening to count the intersection. But if they tell us it's independent, then we can apply the fundamental counting principle on probability by what? this part here is probability of A times probability of B. If A and B are independent, but is it independent? Is it independent? Yes, it says it's independent given in the problem, so that gives me some easy time, right? So that's just probability of A times probability of B, right? Okay, so this part here is because it's independent. So that's take out a pen. I'm going to just use a different color pen. This part here is given, so it's 1/2, and then 1/6. I'm just filling in, and then this part here is 1/2 times 1/6, right? And just basically filling it the formula in. And so then I would have to copy whatever I'm not doing, do the multiplication first because it's order of operation. 1/2 times 1/6. 1/2 times 1/6 is top times the top, bottom times the bottom. So that's going to be 1 times 1 is 1 on the numerator. 2 times 6 is 12 on the denominator. But then now I have to do addition, subtraction, require common denominator. So I'm going to change this first fraction of 1/2 by times 6 top and bottom so that it will have a denominator of 12 and times 2 top and bottom for the second fraction so that it will also have a denominator of 12. And so then this one will give me what? The 6 out of 12 plus 2 out of 12 and then minus 1 out of 12. Now it's common denominator. I can just take the numerator, 6 plus 2 minus 1. 6 plus 2 minus 1 is, what is it? 7, right? 7 out of 12. 7 out of 12. Okay, I don't know what the events are. I don't have a picture. This is not a car. This is not a die, but because it's independent, I can use the formula if I trust the formula now, with the prior examples. So I don't always have to have a picture after I get comfortable with it, okay? So you can see if you want to try it. I think number 7 is very similar. It's very similar to number 6. So let's pause the video and see if you can do number 7, and we can come back and compare answer for number 7. All right, pause the video. Okay, hopefully you have done number 7 on your paper. And it's very important that when we roll the die 2 times, we recognize that it's an independent event, right? It's an independent event because that helps us a lot, right? So this is asking for number 7 is asking for OR. It's asking for OR. So it's the first toss being a 1 and the second toss being a 1. So it's A or B, right? So the first toss being a 1 is 1 out of the 6 choices, and the second one being a 1 is also 1 out of 6, and because it's all, we use addition. But we have to make sure that, do we have any overlaps, right? So because it's independent when we roll the die 2 times, and so that, because each die is separate, right? So, or roll 2 dice that's separate. So then you can use this fundamental counting principle for probability to multiply the 1/6 times the 1/6 and then give us the 1 out of 36. Remember, top times the top, bottom times the bottom for multiplication, right? But when we have a 36 in this last one, we have to make this first 2 36. So I need to times 6 top and bottom to make the first 2 fraction to have the common denominator of 36. So this one, after I times top and bottom, it will be 3 out of 36. The second one, also after I times top and bottom by 6, I also get 6 out of 36. And then this last one, the intersection, is 1 out of 36 because it's top times the top, bottom times the bottom. So when they are all common denominator, I can take 6 plus 6 minus 1 to get 11 out of 36. And that is purely by formula. And because we know what the die look like, if you want, you can actually take out the picture of a die that we saw earlier, right? And so we can say, okay, this, like the first, the red one is the first die, right? So you have 6, 5, 4, 3, 2, 1, right? And the second die is the white one, right? So the first die being a 1, the first die being a 1 means the red one being a 1, and the red one being a 1 is what? Is this column, this last column here, right? This last column here, I'm not drawing very good. That's the first die being a 1. So I counted that out of all these 36 choices, I have 6 of them, right? Because after I make a common denominator, 6 out of 36, right? And then the second die being a 1 is this, right? This first, this top row here, like the white one being a 1, right? The white one is the second die, right? So you see this, I counted 6 for the first die being a 1 on the last column, and the second die being a 1 on the first row, the white one. I counted 6 and 6. You see this overlap here that was counted twice, right? This is the overlap that was counted twice, and that's the one that I needed to subtract, right? So if you were not over counting that corner one 2 times, you count it out, that is 11 out of 36. That's 11 out of 36. So if we could, and if you needed, again, this next exam is a take home, and you have unlimited time, you can actually take out a picture like this and see if it makes sense by looking at the picture. Okay, so take all the time you need to look up what it looks like in a die or in a deck of cards, what a queen, a ace look like, if it helps you. Okay, I know this is very complicated, and if we need to take extra time, look it up. What does that look like? Okay, hopefully that helps. Okay, and so that's exit out of here and come back to number 7. So again, that 11 out of 36, that's how it come about. Okay, so this number 8 is actually from your homework question. Okay, so we have a assortment of 11 machines, and 3 of them are defective with defective switch, right? So draw means to take it out, right? Not drawing, right? Draw means to take it out with or without replacement. So with replacement, what does that mean? It means you put it back after you take it out. You put it back. Okay, and so if you are doing selecting one machine, this is a simple task, right? A simple task. You don't have a given, or you don't have multiple event, you don't have compound event. So your defective one is just what? The element of the defective. How many cardinal number in the defective out of the whole sample space, right? So sample space is any machine, any outcome, any machine, any one that you can choose from, right? So that's 11. And how many defective, right? So this is the cardinal number of the defective. How many defective, right? So that's 3. So this is it if it's just simple event, right? So with replacement or without replacement, without replacement means do not put it back, right? So do not put the one that you choose, do not put it back to the the same place, right? And so if you put it back or not put it back, it doesn't matter because you are not choosing again. And so then your defective one is still 3, right? And your all the possibility that you can choose from is still 11. So the answer to both with replacement and without replacement, if it's a simple event is the same because you are not putting it back or not putting it back. It doesn't change because I'm not doing it again, right? It's not too complicated. So that's the same, right? So if it's just one simple event, the probability of put it back or not put it back is the same. However, part B, if you have 2 machines, that means 2 tasks, right? 2 tasks means we have compound event, and so then we have to think about with replacement means. So what this means for both of them being defective means what? defective 1 and defective 2, right? So if you put it back, you still have 11 machine if you put it back, right? You still have 3 defective if you put it back. So then this is when you put it back, the replacement means you put it back, you still have the same number of choices to choose from. And so that is called the independent event, right? That's called the independent event. So the fundamental counting principle for the probability applies here, right? So then that is, just multiply them together, 3 out of 11, 3 out of 11. You still have 3 defective, you still have 11 total machine. So then that will give you the 9 out of 121. Okay, 9 out of 121. I don't think that's reducible, so that's the answer. Okay, but if you don't put it back, right, again, without replacement means you do not put it back. You keep that machine that's defective, right? So do not put it back. Okay, so then this will be, because you do not put it back, your total number of machine change, your denominator change. So this becomes a dependent event, okay, because it got affected by the first action, right? So your first one being defective, or not, if you don't put it back, your total number of machines to choose from is different, right? So your first one is still you have 3 out of 11 defective, but your second one, because it's dependent, that is actually given, you have to consider given your first one being defective, right? So then your total defective, because you didn't put back, your total defective now is 2, and your total machine, now your sample space got changed. So your total machine, because you didn't put that defective machine back, your total machine is now what? Only 10 of them, right? So this is total defective. If you don't put it back, you had 3 to begin with, but now you only have 2 because you didn't put it back, and your total machine, right, it's only 10 because you didn't put it back. Does that make sense? And so if you were to multiply top with the top, bottom with the bottom, that would be, you can reduce first, right? Or you can reduce after. I think if you reduce, divide by 2 top and bottom, this is 1/5. And so that would be 3 out of 55 for your final answer. Okay, does that make sense? Okay, so this is in your homework question, and if you understand this, you should pause the video now and trying to do part C by yourself and come back to compare answer if you understand what I just did there. If you don't, then you can continue to play the video. Okay, again, with replacement means you put it back, so your total number of choices still the same, so it's a independent event, and independent event means the fundamental counting principle for probability applies here. So if we want defective 1 and defective 2, and then another defective 3, all 3 of them defective, we just simply take the probability of defective 1 times the probability of defective 2, and then times the probability of defective 3, right? And so because we always put it back, so it's still total number of 3 defective and total number of 11 non-defective. I mean the total machine is still, the total sample space doesn't change, right? It does not change. And so you're going to get 27 out of, I believe it's 1331. And I don't think that reduces, I don't think so. So that will be our final answer for that. Okay? So then if you don't put it back, right, don't put it back, then this becomes a dependent event. And so our sample space actually keep reducing by 1 after, right? So probability of defective 1 and defective 2, and the third one also defective, is the first one always is the original, right? So it doesn't get affected by, because it's first one. But your second one get affected because you don't put it back, got affected by first one. And your third one got affected by the previous 2, right? So your third one, given the first one is defective and the second one is defective, right? So your first one doesn't get affected because it's still 3 defective out of the total 11. But your second one got affected by the first one because this is a dependent event. You don't put it back. So what does that mean? That means you only have 2 out of 10 total because the 2 defective, right? And out of the 10 total machine, right? And the third one, you only get 1 left out of the 9, right? So when you multiply them together, the top is 6 and the bottom is 990, right? And I think they are both divisible by 6, so it reduces to 1 out of 165. That should be our final answer. I hope you got this answer. Okay, if you didn't get this answer, you should reach out to me to get help or talk to someone in the class. Okay, that's it for this section. And just to make sure you do see the next page is an extra credit. Okay, so extra credit, it's giving the hint here. It says to make a tree diagram like the last question in 13.3, like the last question in 13.3. I didn't put that down. And then construct a the 2 by 2, the infected, not infected, positive and negative table, right? 2 by 2 table. Okay, so for those of you who is not interested in this extra credit 1 point in this class, now you can just stop the video now. And for those of you who is interested, I'm going to help you start. Okay, so draw a tree diagram, right? 100% is always how we started, and it says to construct one to first do the infected, not infected, right? So if it's 5% infective rate, that means the infected will be 0.05, and then the not infected, right? Not infected will be, because total is 100%, so it will be 0.95, right? Will be 0.95. And then the infected, the infected is supposed to test positive, right? So it says 90% accuracy of 90%. So positive and negative, right? So accuracy, if you are infected, you're supposed to get positive, right? So that is 0.9, and tested negative is 0.1, correct? That's accurate, right? That's accurate. That's not accurate for, right? If you got infected and you test negative, that's not accurate, right? So 90% of accuracy. And then you have what? If you are not infected, to test positive, if you are not infected, you tested positive, that means it's a false positive, right? And so that's not accurate. And not accurate is what? 0.1, and this is 0.9. You're supposed to test negative if you are not infected, right? So that's 90% accuracy. Okay, so if you were to take the 0.05 times the 0.9, that gives you the 0.045. And what does this represent? That's a probability of what? Infected and test positive, right? So that's this much. Okay, so again, if you were to take the 0.05 times the 0.1, what does that give you, right? So that's 0.05. And what is that probability of infected, but what? And tested negative, right? So you can finish that. Okay, so make sure that you know what each one means. This one is what? Tested positive given that it's infected, right? Tested negative given that it's infected. Tested positive given that it's not infected. tested negative given that's not infected, right? So with that, you can finish, and then you can make a table. It says after that, you can make a table of 2 by 2, right? So here, the title is going to be positive and negative, and then infected and not infected. And so from there, you have a total of 10,000 people, a town of 10,000 people, right? So the total infected is 5%, so it should be 500, right? So you can kind of fill it in 500, and then the 9,500, if it's a 10,000, 9,500, that will add up to be 10,000, right? Is it 10,000? Or is it? Yeah, right. I think that's right. That adds up to be 10,000. And then you can say, okay, remember we say 0.045 is positive and infected, so that should be 10,000 times 0.045, so that should be 450. And because the total is 500, right, so that should be 50 here. So you can fill in the table that way and see, then you can answer the question here after you finish the tree diagram and finish the table. Then you can better answer all these questions here. And again, this is for extra credit, so I'm not going to answer questions, but this is a good timeline. If you have someone that you're working with as a group, this is a good one to work together and, you know, to enhance your understanding of this very difficult section, okay? And again, I won't answer any question on the extra credit. You have to work together as a group, but any other question, please reach out to me. And thank you for watching this very hard video and very long. And I hope to hear from you to answer your question. And thank you for watching. See you soon. We are almost there. Thank you. Bye-bye.